So now that we've discussed improper integrals of the first type, the type where we are taking an integral over an infinite interval, we should also discuss the second type, in which an improper integral may arise when the integrand is discontinuous. So we'll spend some time focusing on that case here. And so first we should talk about our motivation for talking about such cases. Sorry, give me a sec. Okay. So first, let's talk about what we mean by discontinuous here, because there's different kinds of discontinuous. So, for instance, we already know how to handle discontinuous functions, really, of the first kind, which is the kind that has a step or that has a removable discontinuity. So, for example, just take this function right here, which doesn't really represent any function necessarily. But this one has a step. So this is an essential discontinuity, but the function doesn't blow up at that discontinuity. So for instance, let's call this f of 1, f of 2. They're the same function, but just we're defining it as a piecewise function. Then if we wanted to find the integral from a to b, we could split it up in terms of two integrals, one for each part of the piecewise function. So in this case, it would just be as easy as separating the integral into an integral from a to c, the left side of that discontinuity, plus the integral from c to b on the right side of that discontinuity. Unfortunately, though, this isn't as easy if the function, for instance, blows up, by which we mean it becomes unbounded. So let's consider that we know capital F of x being the absolute ln of absolute value of x is an antiderivative of the well-known function f of x equals 1 over x. 1 over x has a discontinuity at 0 that's essential, and it's of the unbounded type. We cannot find the area under the curve over -1 to 2 using the fundamental theorem of calculus. The fundamental theorem of calculus only applies if the integrand f of x, 1 over x, is continuous over the entire interval a to b. So we could theoretically think that we can solve this integral. So erroneously, I'm going to notate here that this is not true. Wrong step. We're going to write the antiderivative and evaluate it at b and a. And that gives us ln of 2 minus ln of -1, which is absolute value of -1, so that gives us 0. And that gives us ln of 2. So we would, if we naively took this integral, we would believe that the area under the curve would be ln of 2, but it's not true, because this function has that discontinuity at 1 at x equals 0, and it's essential and unbounded. So here's how we deal with that. Let's actually define then the secondary type of improper integral. We define the integral from a to b of f of x dx equals the limit as t approaches b from the left of the integral from a to t f of x dx, as long as the limit exists, where f is not only discontinuous, but also unbounded at x equals b. Okay? So a great example of this idea is the previous example where we had 1 over x, which is discontinuous at 0. And unbounded, the limit there is on either side is either infinity or negative infinity. So what we mean by that is the limit as x approaches, or I guess we would say the limit as t approaches b from the left in this case of f of t is infinity, whichever one. It could be either one. Then we would say that if the limit exists, right, this limit, the integral converges. Whoops, integral converges. Otherwise, if the limit doesn't exist, the integral diverges. So to give you an understanding of how to make sense of this geometrically, I'm going to draw here my so I'm going to suppose that this is my function. Okay. With an essential discontinuity at some point b. Let's call this b. Let's say this is a. And so if I want to find the integral, I'm going to find some point t very close to b, but on the left of b. And I'm going to find that integral. And then in the limit, as t approaches b, the limit of that area will be the value of the improper integral. So limit of the area under the curve just up to, but not at x equals b, because we can't. It's impossible. But we're hoping then that the additional slivers that we add are negligible in the long run. Now this is a type of improper integral of the second type, where we had the discontinuity at b. We can extend this to being the case where we have a discontinuity at a. So we would take the limit now as t approaches a from the right of t, of the integral from t to b of f of x dx, okay? Where x equals a is the discontinuity. And similarly, if the discontinuity occurs at some point inside the interval, let's call that c, somewhere in the interval a to b, not inclusive, then we define that integral as we split it up, essentially. So as we approach c from the left of the integral from a to t, plus the limit as t approaches c from the right, the integral from t to b of f of x dx. Okay, so this splits it up into two formal definitions of the improper integral. So Again, this is provided all limits exist. So you will have to get comfortable again with identifying discontinuities. And so just to clarify what's happening here, in terms of the example that we started with, right? So the integral from -1 to 2 of dx over x really is the limit as t approaches 0 from the left of the integral from -1 to 0, from -1 to t, I should say, of dx over x, plus the limit as t approaches 0 from the right, the integral from t, or I should use a different letter actually. It doesn't matter too much, but if you're splitting it up, you want to write different letters. And evaluate each limit separately. Both of them have to be finite, though, in order for this improper integral to converge. All right, let's do an example. So we're going to determine whether the integral -2 to 3 dx over x to the 4th converges or diverges. If it converges, we'll evaluate it. So this looks like an ordinary integral, though. The important thing to point out is that we need to see that the integrand, being 1 over x to the 4th, has an essential discontinuity, and an unbounded one, at x equals 0. So I'll have to split up this integral into the form where we have two limits of integrals, where we take the limit as t approaches 0 from the left for the first one and from the right for the second one. So this integral becomes the limit as t approaches 0 from the left of the integral from -2 to t dx over x to the 4th plus the limit as s approaches 0 from the right of s from s to 3 of dx over x to the 4th. Okay, so they have the same antiderivative, which makes it easier. So the limit as t approaches 0 from the left of -1 over 3 x cubed from -2 to t plus the limit as s approaches 0 from the right, -1 over 3x cubed from s to 3. Now, we'll evaluate both of these at the limits of integration. So the limit as t approaches 0 from the left of -1 over 3t cubed plus 1 over 3 to the -2 cubed, times -2 cubed, plus the limit as s approaches 0 from the right of -1 over 3 times 3 cubed plus 1 over 3 s cubed. Okay, here's the thing though. These are constants. This, however, blows up to infinity. What kind of infinity? Well, from 0 we're approaching 0 from the left, so it's negative because we end up getting negative numbers. Or actually, well, rather, it'll be negative and then it cancels with the negative on top, so it actually becomes positive. Similarly, this one, the limit as x approaches 0 from the right, well, positive values, so positive infinity. So this is not in an indeterminate form because we have infinity plus infinity. So we have infinity plus whatever constant stuff that we had. It's infinity, which means the integral diverges. Disappointing, but true. And the limits of integration really matter here. Yeah. So if we had chosen slightly different limits, it's possible that this could have converged. And it just depends on how much or how close you get to the discontinuity on either side. Right, let's do another example. Same idea. We're going to evaluate or determine whether an integral diverges. So we're going to evaluate the integral from 0 to pi over 2 of cosine theta over square root of sine theta d theta. So here, sine is 0, so sine theta equals 0 when theta equals 0. That means we're looking at the kind where the left endpoint is discontinuous, so we're just going to have to do the limit as t approaches 0 from the right, the integral from t to pi over 2 of cosine theta over the square root of sine theta d theta. This one should be a fairly open and shut case because we can use a simple substitution. I'm going to let u be sine of theta. du is cosine of theta d theta. Again, continuous transformation of theta means we don't have to worry about anything with the limit. So we're going to take the limit as t approaches 0 from the right of the integral from sine of t to sine of pi over 2, which is 1. And then that'll be du over u to the 1/2. And so, I'm going to use another sheet of paper here. That will be the limit as t approaches 0 from the right of 2 u to the 1/2 from sine of t to 1. You'll notice now that this is the part where you have to just be careful about what your variable you're working in is. Because we're done with the integration, now we're just going to use ftc2. So we have 2 square root of sine t minus 2 times 1 to the 1/2, so that's going to be 2. And this shouldn't be too bad, right? Because we have, oh, sorry, I have that backwards, don't I? That's going to be 2 minus 2 square root of sine t. Now, sine t and the limit as 0 approaches, as t approaches 0 from the right, that's going to turn into 0, which means I actually have 2 minus 2 times 0, which is 2. That's our answer. And this integral that converges. So that's roughly it. We don't need to say too much more about that.